I think. So we are doing capacitor. In capacitor, we did some basic circuit problems in which we found the C equivalent, and we saw few variety of problem in which we understood the how to redraw the circuit using the concept of equipotential points. Right. This is what we did in the last lecture. So today we'll continue the same and we'll try to derive more formula. Just did I mention some topic that I will cover today? Yeah, fine. I gave one homework. Now I can recall. So there was one question given as homework. Did you solve?
Something like pentagon.
Yeah, that's something like pentagon. Correct.
Sir, I wanted to ask that optics chapter you are going to take, or we have to see the video.
Depending on the time, either you need to see the video. If time will permit, I'll take also. So maybe I can cover in a crash course manner. So detail you can watch. Okay. After wave optics, I'll start the heat and thermodynamics. So what is the C equivalent here? So how we can reduce the circuit? From right or from left?
Same, right?
From right, can you see any series in parallel?
Sir, from left.
From left, correct. From right, so we have the terminal, right? And terminal will prevent you from reducing. So when we reduce the circuit, we cannot affect the terminal. The terminal must be intact. Correct? So reduce from the left and tell me the answer, guys. Everyone, please. So how many of you are able to understand that it will be reduced from left? Right is not possible. Are you guys able to understand that right is not possible?
Yeah.
So if it is not possible, so do you can you reduce from left? Yeah, tell me guys, what is the answer?
It is C by 2.
How much you said?
By 2.
Pardon?
C by 2, hello.
C by 2. So I can see C by 2 and then C is 3 C by 2, 3 C by 2 and C. 3 C by 2 and C is how much? 3 by 5 C, right? And 3 by 5 C. And C is again series combination. 3C by 8. 3C by 8 plus C, which is 21C by 13.
It's a calculation error, sorry.
How you did after that?
Okay, I'll just show you. First of all, you need to go from here. These two RE series combination C by 2.
Yes.
And that is in parallel with this.
Yes, 3 C by.
3C by 2 is okay so far.
Yes.
And 3C by 2 and this C are in series again.
Yes.
So 3C by 2 in C is how much?
5. 3 C by
3C by 5.
Now 3C by 5 and this C are in parallel.
Yes.
Yeah, so 8C
So
by
8 C by 5.
And 8C by 5 and C are in series combination.
30.
So
8C
8C by
by 30.
13, correct?
Hmm.
So we are done till here. No?
21C.
Yeah, and then plus C is 21C by 13 is correct answer. Yes, I think Tanish
By
got the answer.
mistake, I did for the
I got this one.
Okay. So that's a purely reducible circuit and you should have reduced. Now we are going to see some interesting circuits. Simple for symmetrical circuits. So here all values are C. All values are C. So do you see any series and parallel combination? Do you see any series and parallel combination?
I don't think so, sir.
Yeah, so there is not even a single series of parallel. So we don't have series and parallel. So how we are going to solve? So before we solve a circuit like this, we will try to understand the internal process of circuit solving. So what we do is, to understand the process, first of all, we will connect a battery. So no matter how you choose the polarity, it will doesn't matter. So you can just assume some battery. So mentally assume some battery which is connected across this terminal, and therefore one of the terminal is at high potential, other is at low potential. You can think as a 2-point charge, one at high, another at low potential. Now, how many junctions you can see? So apart from A and B, can you see junctions? And if yes, then how many junctions you can see? Tell me. Give me a
3.
guess. Yeah, so we have 3 junctions. One here.
Yeah.
You can also see a line of symmetry, which is prevailing exactly on this line.
Yes.
The line of symmetry is not something a geometrical line of symmetry, rather we call it a electrical line of symmetry, because it will divide the circuit into 2 halves. Even the middle capacitor I can convert into 2 small capacitors, value 2C and 2C, because 2C and 2C in parallel becomes in series becomes C. So I can replace this by this and this, and it will look like a perfect symmetrical electrical circuit. So a circuit with symmetry will have lot of good things, and we'll try to explore how those are, or what are the good things. A junction is a possibly a place where some charge induction take place. So generally junction will have either some plus or minus. Now one thing is clear, that the lines of force, which will, if you think in terms of lines of force, technically the plus and minus will have something like this. If we assume only 2 charges, we have seen in electrostatics, we have
Yeah.
this lines of force. Now this is the typical A and B terminal, and this is the typical lines of force that we can imagine or expect, assuming no other junction is creating the charge. But generally what happens, some charge accumulation take place at the junction. It is quite possible that this may occur minus, this may occur plus, minus, or sorry, plus. And this the one at the symmetry may have something really interesting, and we have no idea what will happen here. Okay, so it may have some charge, it may not have some charge. Let's say if you think as minus, then this is somewhat a difficult diagram to understand. This minus disturbs the symmetry, right? Because for plus this is minus, for this plus this is minus, but this is neither plus nor minus. So I think it's like confusing. I can choose minus also, I can choose plus also. This is the point of symmetry. Now what we need to understand is that whatever charge will come, let's say a battery is supplier of charge, imagine this way. The moment this charge will come here, it will get 2 possible paths to distribute itself. Now tell me first, do you see both the paths symmetrical or asymmetrical? Going through this route and going through this route are same thing or different thing?
See.
So if you go from the top route, the route going upward, before you reach the terminal, how many junctions you have to cross minimum?
One.
If you go this way, you need to cross at least 2 junctions.
Two junctions.
Okay,
Yeah.
okay, yes. Two.
But someone going from the bottom will cross only 1 junction,
Only one.
which means this cannot be symmetrical path.
Okay.
The first thing we need to understand is the two paths are not symmetrical because the end goal is to reach the other junction, the other terminal actually. That is our end goal. We have source, we have destination. And when the source and destinations are well defined, then the route we have to figure it out. Now the various route will have different length or different path length. We count the path length in terms of junction. So you can see that I can go from 1 to 3, and then here. So we are crossing 2 junction. So this is basically a 3-step journey. This is a 3-step journey. This is 3-step journey. So we have many 3-step journeys. So we can say that to go from A to B, we have variety of paths. 2 paths are said to be symmetrical if it will have similar number of steps or steps actually. So definitely I can say that this path and this path are not symmetrical, isn't it? Can you say?
Yes.
So these 2 paths are not symmetrical. So I will say this Q1 charge, I will say Q2 charge. When I'm solving the same question in current and electricity chapter, I will call I1, I2. The meaning remains same. The rate of flow of charge is called current, so it's not a big deal. So I have to break the charge Q into 2 parts, Q1, Q2, and then Q1 will travel further and will eventually go to the terminal B. Now when Q2 will come here, it will again get 2 paths. And definitely these 2 paths cannot be symmetrical. Not because the count is same, because the route is quite different. So if you try to go like this, and if you try to go like this, you possibly pass through junction with a different potential. So these are again 2 separate paths. We cannot call this path as identical path or symmetrical path. The symmetrical path we only see near the terminal A and B. Okay. So again, I can say the Q2 will divide into again 2 parts, Q3 and Q4. Again, Q1 and Q4 will meet at this junction, correct?
Yes.
And after meeting, it may divide again.
Yes.
Now there comes the actual concept. The charge will trace the electric field within the circuit. Okay, charge will trace the electric field within the circuit. Now, if I change the polarity of the battery, what will happen? Do we expect change of field, or do we expect only reversal of field? Tell me.
Reversal.
Only reversal of field, isn't it?
Yes.
Change of polarity will only internally reverse the field. So the path of the charge will just reverse. Okay, just reverse. What does it mean? If I would have started with a battery like this, the charge Q would have come like this, and it must have divided into the same fashion as we assumed on the other side. Yes or no?
Yes.
So when
Yes.
I change the polarity, it will simply reverse the direction.
Yeah.
Which means in case of symmetrical circuit, whatever charge will leave the first terminal, the similar charge will enter the other end. So Q2 must come from here and Q1 must come from here. Is this clear?
Yes.
So symmetricity will force the charge flow to be symmetrical on the 2 ends of the junction. So whatever will leave the junction at A must arrive at the junction at B in a similar fashion. So now I will introduce something called mirror branches. If I treat the line of symmetricity as the mirror, a plane mirror, you can clearly see that left half will be reflected as a right half. So what we can say clearly that this will have the image here, this will have the image here, but this will have the image here, isn't it?
Yes, sir.
And this will have the image here. Do you realize this?
Yes, sir.
And these are called mirror branches, and the rule says the flow of charge or current in the mirror branch must be same. So we cannot assume different current or charge flow in the mirror branch, which means the Q1 will move just like this. Q2 will go. Okay, I'll come to this. Now let's talk about the Q4. The Q4 will come here, but the mirror of this branch is this branch. And as I said, the same charge must flow in the mirror branch. So all of the Q4 will come here, and without getting distributed, will go back here. Do you realize this?
Yes.
Yeah.
So the current will flow like this. One path will be like this. One is like this, and other will be this one. It is clear. So the rules are obvious also and pretty much straightforward. The rules are simple. What are the rules? The current or the charge in the mirror branch must be equal. And because Q1 will go straight to the next capacitor without getting distributed here, and Q4 will go just like this. So this Q4 is not getting distributed at the junction, and therefore this junction which lies on the line of symmetricity is called isolated junction. What does it mean? It means physically it might be looking as connected, but electrically it is not contributing anything. It means there are two tracks. The one track is designed this way, and you design your highway like this. And we know that when you see the service road and some highway, until there is no opening, you cannot be part of the highway. So people moving on the service road will keep on moving like this, and people on the highway. So although it is touching here, but there is a wall actually, and the wall will keep it separated. So it looks like physically they are connected, but they are not physically. They're not electrically connected. The flow of charge will go this way and this way. The same thing is happening there, and therefore the physically connected junction is actually electrically isolated, and for such scenario you can always remove such junction and now you can see this circuit is quite easy to solve because it is perfectly parallel series question, isn't it?
Yeah.
So by knowing the distribution process in a symmetrical circuit, we are always able to separate those junction or node which lies on the point of the line of symmetry. So as a thumb rule, which I'll also mention explicitly, any junction which lies on the line of symmetry never participate in redistribution of flow of charge, and therefore can be treated as isolated junction, and hence we can redraw the circuit with this idea to get a reducible circuit as shown on the right of the this circuit. Okay, so let me mention this as a theory, and the same will hold true for the current and electricity chapter. I will not explain there. Keep in mind that, okay, if I'm teaching something here in a circuit part, I'll try to skip in the current chapter. Okay, so what should I write here? Any junction line on the line of symmetry will never participate in charge current redistribution, means can be treated as isolated junction. Okay. So this junction you can detach. While detaching, you have to be very careful that which part will go with which part. So we know that, or we knew that this was the mirror of this, so these two will be connected together, and this is the mirror of this, so this two. You may ask that, so can we connect like this? The answer is no, because this is not mirror of this. This is not mirror of this. Okay. So just because we have the freedom to detach, it will connect back to its the symmetrical half, the mirror half. Okay. Also, the line of symmetricity is that line which can reflect the terminal. So if you look at this carefully, this line of symmetry is reflecting A as B. So A and B are mirror image of each other. So the line of symmetry must be drawn so that one of the terminal becomes the image of other. If we have line of symmetricity which is not the reflection of the terminal, we cannot take that line as line of symmetry. This is very, very important concept, and one should not forget about it. Is this clear? So now tell me, what is the C current, guys? Okay, now also write some points. So by the way, you can find the answer. What is the C current?
Sir, 7C/8.
Correct. So how many of you are getting 7C/8? Very good. Mugdha, are you getting it? Archit, Kanu, Garv?
Yes, sir.
Aditya?
Yeah.
So you got the answer, 7C/8? Or you're trying? Done, guys? So how many of you got the answer? Raise your hand quickly. When you got the answer? Yes or no? Tanu, you got the answer? All have raised their hand except Tanu. You got the answer? All right. So quickly you can do.
So could you go back to the previous slide? I was writing down the third point. Yeah, thank you. Just a sec.
Okay.
Yeah.
So the next one is similar to previous one. So same question, if all values are C only, what is C equivalent?
Sir,
Yeah.
sir, the branch on the right, is there a capacitor there?
Yeah, of course. I missed it.
Yeah.
Everything.
Sir,
Yes, tell me.
5c/4.
Yes, sir. Got the same.
So I think earlier you got okay, that's fine. So what I have to do? This will go this way, right?
Yeah.
The rest is simple, you know how to solve.
Yeah.
So I think that is correct answer. So let me just confirm C/2 and C3C/2, and 3C/2 and C/2 is 3C/2/4, 3C/8, 3C/8, 3C/8 is 3C/4, 3C/4 plus C/2, which is 5C/4 is the right answer. Correct. Okay, so let me do the another circuit. So all are C. All are C. Find the C current. Tell me, guys.
Excuse me, sir.
Yeah, tell me.
I'm getting the same answer, 5C/4.
5 4. So okay. So what you need to understand here is these capacitors will vanish away because they exactly lie on the line of symmetry. So no charge will distribute. So the charge this will go here. This will go here. So nothing is going towards this, right? Because this charge, whatever it is, will be here. And therefore we have to just remove these three branches and rest you can solve. The answer will be 1 2 3 4 C/4, then C/2 and C/2 and C/4 is 3C/4, right?
See by
3C/4 and C/2 in series, how much? If you read it from top to bottom, C/4 and C/2, that you got the reduction, how much is the answer? CO4 C/2 is 3C/4, right?
3 by
So we are done till here, right? Till here it is 3C/4. And now we have this C and this is C/2 and C/2 in series with 3C/4. Series. What is the answer?
5C/4. Oh no.
3/4 plus 1/2, which is 2/4, 5/4. So it is 3C/10. Am I right? This is 3C/10. And 3C/10 will go with C/2 in parallel. So that will become 8C/10. And 8C/10 will go with C/2 in series. How much is that? It is 13 C/10. 8C/26. And the 8C/26 will go with 2C in parallel, which is 52 plus 8, 60. Is it coming 30/13C? It's just lengthy, but it's not difficult. You can just check. I mean, this is maybe I can make calculation error here also. So check and tell me, guys. Are you getting the answer? You can keep on reducing. You can show it one by one. Reduce, then redraw the remaining part. Then again reduce. Then again redraw the remaining part. If you continue in this process, you will get the right answer without any ambiguity. So what I did here is I just finished quickly. So here the idea was simple. So you can at all see on line of symmetry will vanish. That's it. So you can redraw as either So you're left with only 1, 2, 3, 4, 1, 2, 1, 2, 3, 4. I think one more time, right?
Yeah.
So this is the same question we have done before. So you can reduce from top, right? You can reduce this first, then reduce this, then reduce this, then reduce this part. And then reduce the the last part. And then last you can combine in parallel. So do I need to write all the steps or you can do it on your own? Tell me.
We'll do it, sir.
So the next variety of question is called infinite ladder problem. Also we can call a recursive circuit. So it is inspiration from the mathematics also. So in maths, you might have solved question like this: if y equals to x plus 1 by x plus 1 by x plus 1 by x plus 1 by x plus. So this is the recursive, you can say continued. This is called continued fraction. Continued fraction. And how you solve the continued fraction? So you see the symmetricity, and you know that this entire term, because it is infinite term, so even if I begin from here, this will be same as y. Correct?
Yes.
Yes, sir.
So this is how you solve. You say y equals
Take
to 1
as
by,
one.
and you know how to
Yes,
solve
sir.
the quadratic, right? This is a simple
Yeah.
quadratic. So we are going to solve a similar circuit. So at first go, it won't look like this, but with simple inspection, you will be able to understand. So let me draw it. Okay. So now what is interesting here is the terminal A and B. If you look at the terminal A and B, and if you try to understand the bit of electrostatics again, okay, so you can realize something. If I choose this as plus and this is minus, the lines of force will have only one way, like this. And how the charge will follow the path? It will follow the path of lines of force, right? So because of the lines of force, if you think this way, the electric field is like this. Every charge that will leave the higher potential will definitely divide at the junction, and we have infinite junction here. So something will divide here Q1, and then this will go, let's say Q2. But eventually Q1 will be back here, and this Q2 will travel, all the circuit will eventually when come back, it is again Q2. If I denote Q3 here and Q4 here, then all Q3 will travel the entire circuit and will eventually come back as Q3. And it will meet with Q4, will become Q2. But everything will go back to the destination. So the rule of thumb is, when you design a circuit and when you let it carry the current or charge, and if the terminal shown is like this, they have to return back to B. So whatever will leaving the A has to come back to B. And so it will always, let's say in this case, will move clockwise. It will not go right. So we cannot say that Q4 will come here, will go this way. No, this is entirely wrong. So this is the first part that you need to understand, that how the charge flow will take place. Because at every division, the current which is going further is reducing. So although we have infinite plates going forward, but we have diminishing charge which is eventually to be stored on the infinite possible plate. Are you getting the idea what I'm saying?
Yes.
So as you move, as you progress forward, you do have a lot of plate, but you don't have much of the charge, isn't it?
Yes.
So 90% of charge will come back after 2-3 path only. Then just 2% will store in the remaining 98%. That's very interesting. So the other plates, although we have infinite plate or infinite capacitor, will not make the infinite capacitance. Rather, it will be finite capacitance. And the way to derive the C equivalent is same. So as of now, what I'll do is I'll ignore or I'll pretend that we have only this much. So what I can do is I will just, I hope this is clear. So what I'll do is I'll pretend that this plate, this entire term is a single plate. So if I call this as a hypothetical C equivalent or some C dash, then what is the C equivalent now? So CAB we can write as C dash upon C plus C dash, isn't it?
Yeah.
That's very simple. Oh, no, wait.
Yeah.
I'll pretend then just I'll pretend it like this from here. So if I call this entire term as C dash, this is C, and you can see this C and C dash are in, these two are in series combination. Correct?
Yes.
So what you can write the answer? C equivalent equals to C, the C here is in parallel with these two combination, right?
Yeah.
And that these two are in series actually.
Series.
So can we write like this?
Yes.
Yes.
You can write as C, and then again I'll take the C dash below. So what I'll get is 1 plus C by C dash, like this. And in fact, if you try to replace C dash with the remaining part, it will eventually become a recursive circuit. Similar to that. always. So of course, this is the recursive circuit at the end, but how to solve this? We take the advantage of infinity, because infinity minus 1 is infinity. If I
Infinity.
remove one of the branch from infinity, it will really not affect the answer. So what we can say that if I choose this as terminal, let's say terminal P and terminal Q, then I can say that the equivalent capacitance between P and Q must be same as equivalent between A and B, isn't it? If I cut it from here, because even if I remove from here, I can see the right side circuit is similar to the circuit which we had actually,
Yes.
and subtracting one of the branch will not affect the answer, isn't it? So
Yes.
the C equivalent across PQ, if I call it X, then C equivalent across AB must be X. Can we say yes or no?
Yes.
And therefore, the X must be equals to C plus Cx by C plus X, isn't it? I can choose this as X, so this will become, if I redraw, C, C, but this I can replace by X. And we know the net answer is equivalent of, the net is again equivalent of X only, right? So
Yeah.
the CAB is X. So if I write this is Cx by C plus X into plus C, and this is the equation. This is the recursive equation, which is very easy to solve. So can you solve and tell me the answer? Can you solve, guys?
Yes.
Do it. So do you realize the recursive relation here? Yeah. So solve for X. It's a very famous answer. The answer is called, I'll tell you.
Hello.
Yeah, tell me.
P plus minus root phi C by 2.
Very good. So X turns out to be how much? Root 5 minus 1 by 2 into C, right? This is what you got?
Yes. Just right. But plus minus.
What you have to take only plus, no minus?
Yes. Yes.
Is this clear, guys? I hope you all are getting the answer. And this is actually called the inverse of golden ratio.
Sir. Hello.
Yes, tell me.
Sir, I'm getting opposite 1 minus root 1.
Yes, sir. I'm getting 1 minus root 5.
Very sad. I need to solve them. But nevertheless, I'll solve. Okay, so we are getting X equals to C square plus Cx upon C plus x, which is Cx plus x square equals to C square plus 2Cx. So x square minus Cx minus C square equals to 0. X is minus b plus minus b square minus 4ac, which is, so we are getting c plus minus root 5c. So minus b cannot take, so answer must be plus, right?
Yes, sir.
Make it plus.
Ah,
So the answer will be plus actually.
Yes.
So root 5 plus 1 by 2 is called golden ratio. Yeah, that answer is 5 then.
ah.
No, I think this is 1 by 5. Yeah. This is golden ratio. Yeah, correct. Pi is basically root 5. No, this is plus plus. I was getting confused. So value of value of golden ratio is 1.618. I think this will give you 1.618 plus. Root 5 plus 1. Yeah, 1.618 is correct answer. So this is the 5. This is called golden ratio. And in physics and mathematics and in other branch of science, the golden ratio plays a very vital role. It is like the beauty of nature hidden in mathematics. You can read more about golden ratio. Okay. So this is the, okay, then you can make a variety of changes. You can create something interesting. So recursive circuit can come with surprise also. Surprise means it can be challenging. Repetition with some variation. So imagine if I have a, so the, we have, it's infinite. Okay, it's like this. You can keep on drawing the triangles inside the triangle, inside the triangle. But what is interesting here, that every time you enter the triangle, the C becomes double. But if you enter, okay, and then if you enter, so you can do something like this. And then this will become 4C, 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 like this. and this will continue infinitesimally, like infinitely, for infinite time, you can say infinite time. So can we find the answer for the C equivalent? Okay, is it a symmetrical circuit? Yes or no?
Yes, sir.
And if you look carefully, every junction which is lying on the line of symmetry will have disjoint connection. So you can remove it. Although it looks touching it, but you can remove it. So in reality, it will look like a big one, but this branch will remove here. It is not touching it because it's disjoint. But for this branch, this is not touching, so it is disjoint. This is disjoint, and so on. Okay. So this is the first observation, that the line of symmetricity will make sure that those junctions which are part of line of symmetry will not contribute in a redistribution of charge or current, hence can be separated, isn't it? Is this clear, guys? Is this clear?
Yes.
Okay. Now, how to solve question like this? Imagine the answer across A and B, let's say A and B is coming X. So it will be having format something into some number into X, isn't it? I mean, that number could be anything. So the answer will have the format some K into C. But if I start from this point, if I would have started from C and D itself, ignoring the outermost triangle, the answer would have been the number into 2C, isn't it?
Yeah.
Yes.
Which means if I choose this answer as X, this will become 2X.
What?
Which means I can replace the entire answer by a capacitor like this, but I can replace this by 2X. And thus now you can write X equals to the CAB. What is CAB now? You can reduce it, C by 2, C by 2 and 2X. So 2X plus C by 2. 2X plus C by 2 is in parallel with C by 2, series with C by 2. 2X plus C, and that is in parallel with C by 2, and that is equals to X. Tell me guys if I'm wrong. Kanu, my voice are audible to you?
Correct.
Yes, sir.
Kanu, my voice audible? Hello, hello. Kanu, are you there? Am I audible to you, Kanu? Yes or no? Okay. So if you solve this, you can get the answer X. So is it possible to solve this and tell me the answer?
Yeah, just a second.
Hello,
Tell me.
sir, I got 1
Plus root 7 by 4
plus root 7 C by
whole by 4. Yeah, into 6.
yeah, same.
Very
Yes,
good.
sir,
I think this is
also
the
good.
right answer. This
Yes.
is the right answer. Yeah. All right. Okay. My voice is clear to all of you, no? Are you able to hear me?
Yes.
Yes, sir.
So after the ladder problem, we can go to something called problems based on folding symmetry. No,
Sir,
whenever
have a
I,
doubt.
pardon?
Hello.
Yes, tell me.
I have a doubt. Means how to understand in exam that this problem is of this type, like infinite ladder problem or something.
So if it is infinite ladder, it will look like infinite ladder.
Oh, okay.
It's simple.
Okay.
And also the values will be repetitive, so you can understand that the answer is going to be same.
Yes.
Okay. Even the values will vary. They'll make sure that it is varying in some fixed ratio.
Yes.
So that if one answer is x, other is either x by 2 or 2x, something like that. So circuit is, I mean, something which comes through experience. It is neither difficult nor easy. And the more you have seen circuit in your life, the better you can guess in the examination. But don't worry, the JEE, as far as JEE concerned, the questions are so trivial that 99% question you can solve mentally. It is so trivial. And with the time, you will see some really advanced method of solving circuit. So just keep patience. You're going to see something more deep. So problems based on folding symmetry. Now, if we have identical set of capacitor arranged in a way which looks really fascinating, I'll draw one of them. So you can see we have a circuit, and let's say every segment represents so this is the condition. Now again we do the same mental analysis of charge flow. We do see some really nice symmetry. Symmetricity is not just of circuit. So this is definitely a line of symmetry without any doubt. But also, if you look in terms of values of capacitance, it is so symmetrical that whatever charge will arrive here will find both the paths symmetrical, isn't it?
Yes.
Do you agree?
Yes, sir.
So coming to this point, the charge will become Q by 2 and Q by 2 for sure.
Yeah.
And therefore, I can say the potential of this junction, because we have similar charge, similar capacitance, and we know the potential difference is Q by C. So can we say the difference between this point and this point and this point? So 1 and 2 and 1 and 2 dash will have same potential difference, yes or no?
Yes, sir.
Because of the charge flow. If I assume the charge flow, it will force us to believe or think that the potential of 2 and 2 dash are equal, isn't it?
Yeah.
And similarly, by the same logic, if I distribute the current charge further, now I won't say this path and this path are symmetrical. No, this is not symmetrical because this is some midpoint. But what I know is that whatever charge will go here and whatever will go here, Q dash, the same will happen here, the Q dash and Q. Okay, I have taken the Q dash. Some other name. Q1, Q2. So if same in a similar fashion, when QY2 will come here, the Q2 will go here and Q1 will go here. But no matter how the charge we have to distribute, it will have a very symmetrical pattern. And therefore, I can also say the 3 and 3 dash junction or node will have same potential. Yes or no?
Yes.
Yes, sir.
And so the 4 and 4 dash without any doubt, then 5 and 5 dash without any doubt, and then 6 and 6 dash without any doubt.
Yes.
Now, because they are having same potential, so 2 points at same potential, we can either disjoint, we can separate them like a chewing gum, which you can elongate, or you can also connect back. So if you connect back 2 with 2 dash, 3 with 3 dash, 4 with 4 dash, 5 with 5 dash, and 6 with 6 dash, what is the thing? The entire circuit will fold about the half, isn't it?
Yes.
And that is why in such scenario, we talk about the folding symmetry. See, I'm not saying you're supposed to remember these names. You understand the logic. Then automatically you can fold it into half. Why? Because we are trying to reconnect back the same potential point. And the moment we see such situation in a circuit, the circuit, once you fold it, right now you can see that there is something you can't see any series of parallel. Do you see series parallel right now?
No.
Only few, like this part is series, but it is still complex. Okay, but the moment you fold it, you're left with only one half of a circuit. Something like this, isn't it?
Yes.
But there is a change here because of the overlapping. If the capacitance in the actual was C, now every capacitor here will become Y2C. Can you guess?
They will overlap, right? So
They will be in
it will
parallel
be total
combination.
to
Parallel
C.
combination.
Yeah, because they are now in parallel
Yes.
combination.
Ah.
The overlap will create parallel composition of circuit. And those parallel combination will become 2C, 2C, 2C. So that is the change which we need to, bring while we transform the circuit using folding symmetry. Is this clear? And now if you look carefully, you can solve this mentally. What is the answer now? Come on, guys, this is pretty easy to solve.
C/2.
So much time, man. This is so simple. C by 2 is the right answer. This was like a mental calculation, right? So these two C will become C,
Yeah.
Yes.
C, and then C, this C, 2C in parallel, so this is 2C.
Yes.
2C, 2C again C, and 2C, 2C, C, 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 C.
Yes.
All done.
Yes.
Why it was taking so much time? Okay.
Sir,
Yeah.
I didn't understand this one.
Explain like what you exactly will get. The 2 and 2 dash, what you are supposed to do, 2 and 2 dash overlap.
Yes.
Imagine it is like the push button. You know, in some sweatshirt or some jacket, you get a button, the lock which you lock. So you press it against one each other and it gets locked, right? So imagine 2 and 2 dash R button. So if you connect it, what you'll get is from this line, from the line which we have done, we have two things. I can just do like this parallel button connected. Okay. Then what you get is 2 button here, 2 here. Do you realize this?
Yes, sir. Okay.
So this is the actual circuit, isn't it?
Yes.
Which we can draw better by, okay, because both are in parallel. I hope you understand what is going on.
Yes, yes, I got it.
Excuse me, sir.
Yes.
So if we were to fold this figure again and get it like make
No,
the capacitance, no?
see, the rule is you cannot fold by altering the terminal. See, our terminals are intact, right?
Hmm.
So
Now the terminal will
every transformation, see, always remember, every transformation in circuit should not affect its terminal.
Okay. Sir.
That is thumb rule. If you are trying to achieve some sort of folding or some sort of restructuring of a circuit, and while doing the restructuring, if the terminal gets affected, it means it is not the same circuit. So this is the you can say thumb rule of transformation of circuit.
Okay. Sir.
Okay.
Yeah.
So I know you were thinking about this line, right?
Yes, sir.
Yeah. That's okay. Very common mistake we have to avoid.
Okay. Sir.
The next is, and see, if you look carefully, what I'm trying to do is I'm trying to give you a charge distribution before I try to give you the logic. So also when you come across a new circuit in which something is very new to you, always go through the charge distribution, think about it as much as possible. And of course, for the varieties which you're going to see in this chapter anywhere, that kind of variety I'm going to discuss here. The next is I'll call the Q problem. So we are going to solve a three-dimensional problem. So every branch is C. And I will number it. So in every Q problem, there are three things which we generally ask. The first is called between any edge across any edge across any face diagonal across any body diagonal so you can start. Okay, we will not start to solve because solving is easy. What really we want is, okay, I can give you the very shortcut idea to get the answer, but the reality is, okay, we are not looking for answer, we're looking for something more deeper. How to think from scratch. So I'll go with the first case. I'll choose 1 and 2 as my edge across which I'll try to determine. For face, I'll choose 1, 3, which is easy. For body, I'll choose 1, 7. So let's redraw and so before we proceed further, we have A and B as our terminal. Everything is C, so I'm not representing it. The first step of analyzing anything new is assume a hypothetical cell connected and assume some charge coming from the cell. So coming at the junction, how many paths you can see?
Three.
And do you believe that any of the paths is symmetrical?
Yes.
Which path?
Any three.
So anything, all three are symmetrical. You mean to say 1, 2, 1, 4, 1, 5, all are same?
No. No.
At that junction, which path you think is going to be similar? See, you have to eventually
1,
come
4
at
and 1,
yeah, 1, 4 and
1, 2.
are symmetrical. See, 1, 2 is directly coming to destination. It is like you start the
Okay,
journey, you end the journey.
yes, correct.
And 1, 4 is going through longer path, right?
Correct.
So look for a while, try to absorb the picture in your brain, and then I'll comment.
Sir, I think two symmetrical paths.
Yeah, all right, which one?
So first is 1432 and then 1562.
Excellent. These two are exactly symmetrical paths.
Yeah.
So how many of you are able to see it? The symmetrical path.
Yes. Got it.
Okay. So if you can see the symmetrical path, then the charge will distribute equally in those symmetrical paths. Like from at a junction 1, the 1, 4 and the 1, 5 must get the same charge.
Yeah.
Yes or no?
Yes.
So if I say the charge in the path 1, 4 as Q1, I must call 1, 5
Q1.
also as Q1.
Yes.
Yes, sir.
always learn this process because rest are easy. I mean, what we are going to solve. See, circuit solving is not a big deal. What is the big deal is writing the charge. So if I call this as Q1, I must call this also as.
Q1.
I don't know what will happen in future, but at least at this junction, I can say with 100% confidence that these two must have similar charge, no matter what is the value. I don't know, and this will have a different value, Q2. And Q2 must be different now because you're going from source to destination just like that.
Yes.
The other thing you can see is that the Q1 will go here and return back. And these two are exactly same path. Can you realize this? This is same path. Technically, these cannot be different. If you look from the terminal side, if you look from A and B, these two planes are same plane, isn't it?
Correct.
Do you see any difference in the two planes? I mean, I don't see any difference.
No.
If you see, let
No,
me
no.
know. So these are exactly symmetrical planes, and therefore they will follow some simplicity. The other thing is because we are solving a circuit in which every values are equal, and we have talked about line of symmetry in 2 dimensions. Similar to that concept, we do have something called plane of symmetry. So do you see the plane of symmetry? Here you can put an actual mirror in a 2-dimensional mirror, and it will form the half of the circuit as an image.
Yeah.
So where I should have put the mirror? Can you guess?
So like vertically, the mirror should pass through the midpoints of 5, 6, 7, 8, and 6.
Correct, correct. Very good. So definitely this is the mirror part, right?
Yeah.
So do you guys see the mirror?
Yes.
This is the mirror. And therefore you can clearly see which branches are mirror images of each other. I can see the 5, 8 will have the mirror image with 7, 6.
Yes.
But one will be going from 5 to 8, but other will be coming because they are on the other side of terminal, right? And the meaning is whatever will leave the 5, 6. I mean, right now I don't know. Okay, I can say something. Okay, let's talk about the first junction 1. 1, 5 will have mirror image. 1, 5 will be similar to
2, 6.
2,
2,
6.
6, but it will come back.
Yeah.
Yes.
1, 4 will be similar to
3, 2.
2, 3.
Opposite direction. Yeah.
Yes.
I can again say Q1.
Ah.
So now if I choose this branch, the mirror will be this one.
Yes.
Yes.
Okay. So what I'll do is, if I assume this as Q3, this must be Q3.
Yeah.
And because Q2 and sorry, if you come at this junction, what is coming? Q3 is coming.
Yes.
Q1 is going.
Yes.
Okay, what must come here? What must come here? See, Q1 is coming here, and Q3 is leaving. So out of Q1, Q3 has left the junction. What must be going here?
Q1 minus Q3.
Q1 minus Q3.
Now you can see Q1 minus Q3. If you add Q3, it will add up to Q1 automatically.
Yeah.
The incoming and the outgoing are equal. Can you check?
Yes.
You can definitely check. Okay.
Yes. Yes.
And now we have no idea about the other one. So, but I can say one thing for sure, that uh, this will have we need to assume something new. We can assume the tutor. Okay. Okay. So what about the last branch? I mean, just if we can crack that value, either we need to assume something new or we can do it with the same. That is, I'm thinking.
Which one?
Okay. Now this is symmetrical because I think this is also Q1 minus Q3 because these two branches are same, right? We have discussed, no? This path is same as this path.
Yes, yes, yes.
Yeah.
Yeah.
So that is also going to be Q1 minus Q3. I think now we can get all answers without much difficulty. So this is Q1 and this is Q1 minus Q3 going. So what is going here?
Q3.
Q3.
So what will come here?
Q3.
Q3.
Yeah. Okay. And then what will come here?
Q3.
This is how much? Q1. And that is again because this is no. This is my bad. Q3 coming. Q1 minus Q3 coming. Sorry. Q3. This is 2Q3. 2Q3. This is Q3 coming here and
Yeah,
Q3 coming
yeah.
from here.
Yes.
Yeah.
So this is twice of Q3. Just I will write cleaner so that you can read. This is twice of Q3. And now it is satisfying everybody. Now you can see at every junction, indirectly we are satisfying something called Kirchhoff's current law, or it's simply the incoming charge and outgoing charge is same everywhere. Do you see that?
Yeah.
And do you realize that?
Yes.
So your homework is do it without looking at it. I'll come back to the same question after some time.
Yes.
Try to do on your own in your
Okay.
notebook. Everyone will do it. This is the toughest part you are doing in circuit. Toughest part. The rest is something, I mean, trivial. And JEE questions are trivial. Don't worry about JEE.
Hello.
Yes.
Sir, I think I did it again.
Yes, sir, me too.
Very good. So if you're able to do it again on your own, it means you now know the exactly what exactly goes in a circuit, how the charges are distributed, and how we can exploit the use of symmetricity. So basically, when you solve a tough question in because there are very few, but there are questions, you need to first understand the symmetry. And once you understand the symmetry, you can probably distribute the charge in a simpler and neat fashion so that you can write the equation in a circuit and get the answer. So we'll see that later on. But right now, we are supposed to solve this question. So once you have done this, coming back to this problem, you can clearly see something. You can see the isopotential points again. Because I can see 1, 5, 6, 2, 3, 4, 7, 8. So at junction 1, you can see there are two paths with same charge. And if the charges are same, then we know potential difference is Q by C. Because C is same and Q is same, we can say potential differences are same. And therefore, you can clearly see which 2 points will have the same potential. Can you see the isopotential with respect to junction 1?
So 1, 4 and 1, 5.
So the isopotential will be 4 and 5.
Yes.
And similarly, the other will be 3 and 6. Isn't it?
Yes.
Do you see 3 and 6 having same potential?
Yeah.
Because they have same charge and they are carrying the same current. They have same capacitance, right? So if 3 and 6 having same potential, we know in any electrical circuit, 2 points having same frequency, same potential can be joined together, isn't it?
Yes.
And if you join together, joining the isopotential points, we can see something really interesting. It is again like a folding symmetry, like it is you're in a way of folding it. So 5 will attach to 4, right? And 6 will attach to 3. So how it will look like after getting connected back? It will look like something like this. 2, do you see this? The 8, 5, 4, or you can either you can do this, or you can what you can do in next is you can draw the isopotential points on a paper. So I think 1, 2, then I think 5 and 4, then 8 here, I think 7 here,
3 and 6.
and 3 and
3
6. And you just need to draw the capacitor between them. So we have 1 here, but we have 2 here, right? Then 2 here. Am I right, guys? Tell me yes or no. Okay, I think you're not realizing that. Are you guys getting this? What is happening here?
Yeah.
Yes, sir.
Very good. And now we have one answer between 1 and 2. So now, now we have capacitor. This will look like very nice if I can draw in a this manner. In which this is C. So few are C and few are 2C. Can you identify the C part and 2C part?
So one's from 5436 will be You see?
So I think this is the circuit, right?
Yes.
Yes, sir.
C, 2C,
That.
2C, 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 C,
See.
and nothing. And you know how to reduce it. So tell me the answer. So try to mentally collapse the circuit and try to visualize the diagram that could be possible. And with your own visualization, try to plot on the paper, you will get the right answer. So yeah, it demands some sort of visualization ability to reduce the circuit. So for many, it will be difficult if you find it really hard to visualize.
So is it 12 by 7C?
Yeah, I think that's correct. So it is 12C by 7, right?
I think so.
Yeah, this is the right answer. So those who are done with the 1 and 2, try to do the 1 and 3. Try to bring the logic again, try to think of symmetry, try to distribute the charge.
Means
And before you
again, you
solve,
have to do the same thing, like
yeah, I
charge.
mean, you have to think about everything, distribute the charge, like do whatever it takes and try to get the answer. Even if it takes 15 minutes, I'm okay. But make sure that you go through it. But this is the part, if you do not go through right now, you will never learn how to master circuits. Okay, so you spend some time for the next part. Everyone, please
Sir,
Yes.
sir, can you show previous slide, Means?
But this new branch, or the, you can say, the new terminal will have a new distribution of charge, right?
Yes, no, I wanted to see the numbering of 1, 2, 3.
Okay, numbering you can choose whatever.
Yeah.
See, just 2, 3 questions. If you just practice hard enough for 2, 3 questions, that idea will actually start seeding, in your brain. So you will have the comfort, with other questions. But this is just a beginning. I mean, few questions and you're good. Done, guys? So for 1 and 3, how to look like? Do it fast. So let me draw this quickly. Now this time our terminal is 1 and 3. So it is very easy to see the line of symmetry, right? Plane of symmetry.
Yeah.
And this plane of symmetry is obvious. This one, right?
Diagonally?
Like this, no?
Yeah.
See, we always look at the plane of symmetry in terms of terminal, right? So for this plane mirror, and though everything is not symmetrical, you can see there are two branches which is part of line of which are part of plane of symmetry. We know that any node which lies on the or any junction which lies on the plane of symmetry will never participate in redistribution of charge. So, okay, first of all, the bottom two will be same or different. You can see both are equidistant away,
Same?
two path away.
Yes.
So there is no ambiguity. So I think this is same Q1, Q1.
Yes, correct.
And this we can call Q2, and then we are done. Q1, Q1, Q2, because these are mirror branches, and therefore nothing will go from here, nothing will go from here. These two branches are of no use. And Q2 will again divide equally, Q2 by 2, Q2 by 2, same here. So this will look like a simple circuit. And the branch joining the bottom and top is gone away, right? And I hope this is pretty easy to solve. So what is the answer, guys? Tell me.
Excuse me, sir.
Yes.
I did not get this part. Like when we take the mirror, why those two branches will be useless?
Okay, because the if you look at the mirror branch, this is same as this.
Hmm.
Similarly here.
Yeah.
So they must carry the same current or same
Huh.
charge.
Huh.
So nothing will distribute here. No? This will go like this, will go
Okay,
like
yeah,
this.
fine.
And
Got it.
same is for here.
Yes.
So this
Yes.
this connected branch will carry nothing actually.
Okay. Got it. Thank you, sir.
Sir, is it 4C by 3?
Yeah, it's 4C by 3. Okay. Also, you can see that the 2 and 6 will have same potential. No. Okay. Anyway, or 8, 6 will have same potential. So you can also redraw as 5, 8, 5, 6, 8, 7, 6, 7, like this. Then 6, 8, 8, 4, 1, 4, 1, 2, 4, 3, 2, 3, 7, 8. And now this is again symmetrical. I mean, if you look carefully, this is again, I can reduce as simple 2C, 2C, C, 2C, 2C, C, and 2C. So at first go, you may call this is symmetrical branch is there, but now you can further replace, right? Because the 2C is on the line of symmetry, na? You can see. And
Yeah.
because 2C lies on the line of symmetry, it will vanish.
Yes.
So what you're left with is just 2C, 2C, C, 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 C by 3, and C, 4C by 3. Yeah, that's correct. Is this clear, guys? That distribution part is clear.
Yes.
So it is easy to figure it out that which branch will carry nothing.
Yeah.
Now the last part is the body diagonal. Can you try this part at least for me? So solve for body diagonal. What is the answer? Tell me. Is it done? You can easily redraw the circuit. Now you can see the.
I'm not
The
able to make the circuit.
pardon.
I'm not able to make the circuit.
So
Yes,
not able
yes,
to make the
yes.
circuit. What you are able to make? You can draw the cube, na?
Yeah.
You're able to draw the cube.
Yes.
In the cube, you have to distribute the charge at the junction of the terminal.
Mm.
So at every junction, we have three paths. Can we differentiate the paths?
Yes.
So our paths are symmetrical or asymmetrical.
Symmetric.
And if all paths are symmetrical, then charge will distribute equally.
Equally. Yes.
And on the other end of the terminal, all will come back equally.
Yeah.
Here we don't have any line of symmetry. We don't have any plane of symmetry. What we have is only symmetry.
Okay.
Symmetry of logic, symmetry of path. So if you distribute the current carefully, you can see the answer. And if you move further, you will see even at the next junction, again the two paths are symmetrical, isn't it?
Yeah.
Yeah.
So it will divide again. It will divide into half value. So if you have taken Q1, Q1, Q2, sorry Q1, 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 at the very next junction it will become Q1 by 2, Q1 by 2. Can you see that? Can you see that? Yes or no?
Sir, I am unable to see that.
Okay. So I'll just to make it interesting and easy, I'll take this terminal A and B. Okay. And if you take A and B, you can see whatever will come here will divide into three parts equally, right?
Yes.
Yeah.
So Q by 3.
Yeah. You're right.
And so the same will come here.
Hmm.
Now because of symmetry, because of the path symmetry. Now if you come here at this junction after traveling Q by 3, these two paths are exactly same, no? To reach
Yeah.
the B, Q by 6.
Okay, got it.
Now you repeat the process for all these three.
Q by 6.
Q by 6.
And for this also. I think all are done now.
Yes, sir.
All branches are done.
Yeah.
Now, can you identify the equipotential points? I can see clearly. And should you see clearly? So you can redraw the circuit in a similar fashion by drawing the iso potential points, then redrawing the circuit and getting the answer. Can you do it for now? Can you guys do it now?
Yes.
Okay, go ahead. Yes, Kanu, am I audible to you? Kanu?
Sir, is it
Yes.
6C by 5?
Yeah, that's right answer. Very good. Is it done, guys? If you remember the numbering, I think this was 1, 2, 6. So 5 and 3 are the two extreme. Then 8, 6, 1. 8, 6, 1 is one particular point, isotensile point. And then 7, 4, 2. 7, 4. So I think this is the diagram, right? So between 5 to 8, 6, 3, we have 3. So 3C, 3C. And between 8, 6, 1 to 7, 4, 2, you will get 6. There are 6 capacitors. 3C, 6C, 3C, right? Three C and 6C will become 2C, 2C and 3C, 6 by 5. Any doubt in this, guys? Tell me.
What?
So you are only supposed to redraw the circuit, and once you redraw, you get the answer. Okay.
Yes.
Anyone having any doubt, please raise your hand. I will try to explain again.
Sir, I do.
Archit, you understood?
Sir, I have a doubt.
Okay, tell me.
So like the equipotential points, I think it should be 1, 2, and 4. Like one equipotential point should be 1, 2, and 4.
Now, why 1, 2, and 4?
So capacitance is C and Q by 6 is flowing across both.
So 4 and 2 you can say, not 1 to 4. 1 is
Yeah.
different and 4 and 2 are same.
Okay.
Okay.
So you can anyway see 4 and 2 are same together only.
No, I was getting confused with 1 actually.
No, 1 is different. 4 and 2 are
Like it
same.
is flowing to 4 and 2.
Yeah.
Okay.
So you begin at 1. So
Huh.
1 will have 1 is the one of the terminal, and 4 and 2 are the other terminal. So 4 and 2 will have same potential.
Got it.
And then how come 7?
How come?
4
7.
2 I got, and then 7 also.
So for B point, for this end,
Yes.
7 is one step away.
Huh. Okay, huh. Got it.
So I didn't get it.
For this terminal,
Mm.
this 7 is same step away as 4 and as 2.
Yeah.
So they
Okay,
are having
okay,
the same
okay.
charge.
Uh-huh.
So they are having, see, you start here,
Hmm.
you carry same charge, you end at the same point. So this is same for all, but so this also
Yeah.
be same for all.
Yeah.
And so for the second terminal, like 5, we have 8 6 1.
Yeah,
Ah,
8
got it.
6 1.
Huh, got it.
Correct. 8 1 6.
So first we will write both the terminals and then we will see what is going on.
Yeah, then we can
Yes.
redraw the number of capacitor between them.
Got it.
And then once you do it, it's easy.
Yes, got it.
So later on, we are going to solve this by various other methods. That's why I have shown you the charge distribution. At home, you all have to practice enough to get a intuition of charge distribution. Okay? So that intuition is very, very crucial. And then now we can solve something. So see, now there are many things, many types of distribution. We have some more complex circuit methods also. So we have something called grid problem, just for your grid problem. So we will take a simpler circuit like this. So every segment is representing one C. Yeah. Yes. Please, those who are having class can leave. I will also leave in 5 minutes. So this is the last question. Now, of course, these kind of questions are not part of JEE, so no need to worry. But because it is given in IITJEE, and so while solving, it's good to know it's not difficult. So here we use a new concept in circuit theory called principle of superposition, and according to this principle, this is the terminal. Say, if you want to find the C equivalent between A and B, so generally what we do is A and B is connected to some sort of imaginary black box. This is called the black box model. We don't know what is inside. So what we know that from inside we have two connections, and these two connections are available to us. Let's say the battery is now whatever is inside I don't know, but I know this is a battery, this is a charge cube. Then for these 2 points, the equivalent we can write as, so C equivalent we always write as charge given by the cell upon potential difference, right? This is the formula.
Yes.
So we are going to employ the same. To do so, because I will assume the potential difference of V across A and B, so that can be achieved by assuming the A at plus V by 2 and B at minus V by 2. Now, what are the benefits? So as per the principle of superposition, the net charge or current in any branch is equals to the superposition, or you can say algebraic sum of charge or current, assuming if only one source is present at one time and all other sources are short circuited. Let me put in words. According to this principle, the net charge oblique current in any branch of a circuit is equals to the total algebraic sum of charge current, assuming one source is present at once and the rest are short circuited. Okay, it is not properly worded here. I think I made some grammatical error, but anyway. So here what I'm trying to say, according to this, the net charge in any branch is equals to the algebraic sum of charge current through the branch, assuming one source is present at once and rest are short circuited. Yeah. So either I assume potential difference V and Q, which is going from here, or I can assume, let's say at once Vy2 is connected. If Vy2 will give charge Q, how the charge will distribute? Because it is infinite grid. This is called infinite grid. So the charge will have 4 equal paths, isn't it? Do you realize the number of paths?
Yeah.
So each path will contribute 1/4 of charge. Yes or no?
Yes.
Now similarly, if I would have applied minus V/2 at this junction, we can expect plus Q/4 coming towards this, assuming the
Yes.
other is not present. So if I only look at one of the source at once, I can clearly see the net charge through the branch or desirable branch. And by the principle of superposition, what is the total charge through the branch? You can see it's Q/2.
Yeah.
Okay.
Yes.
So now we know, no matter what charge is going, what is will flow from here to here is
Q/2.
Q/2. So if I choose this as, because this is capacitance C, so Q/2C. So what we can say? The V must be equals to Q/2C. The potential across will be how much? Q/2C, isn't it?
Yeah.
And what we are looking for is C equivalent, which says that Q/V,
Q/V.
which is 2C.
Yeah.
Okay. So the formula is for a grid, we write a formula like NC/2, where N is number of branch at any junction.
But every time it will have 4 only, right?
No. It
Or
means
different.
if I draw, let's say, just a moment. Imagine if I have the graphite shaped circuit. You know graphite? Have you heard graphite?
Yeah.
Yeah. Hexagon.
Yes.
If I repeat it in two-dimensional space infinite times, Looks like honeycomb. No?
Hmm.
Anyway. So if this will repeat infinite times in all direction. This is again infinite grid circuit, right?
Yeah,
And what you can see at any junction now, it will be q by 3.
3 branches, right?
So if I choose here, then the branch this will become 2q by 3.
Yes.
Q by 3 because of the other, right?
Hmm.
And therefore the C
3C
equivalent
by
will get is 3C by 2. That's why I said NC by 2. What is N here?
Number of
Number of
branches.
branches.
Number of branches. You can see there are 3 branches. So
Yeah.
3C by 2. Earlier it was 4C by 2. That was the answer was 2C.
Mhm.
Understood?
Yeah.
So I can
Got it.
create for any like something like this slightly difficult. And it's not easy. The manual drawing is an issue actually. But anyway, you can see at every junction we have 6 branches now.
Yes.
Do you see this?
Yes. So 3C.
So 3C.
Got it.
Okay.
Yes.
So this was the. Now there are many more. There are many more variety we'll see in the next lecture. They're not much, but I'll give you 2-3 extra idea, and then we can directly go to circuit, how to solve circuits. Okay.
Okay.
So I'll stop today here and see you on Tuesday.
Sir,
Thank you,
I
sir.
wanted to ask one thing from you. Now
Yeah.
here we are doing capacitance, right? So we should start optics also now, right?
Yeah.
Like
So
I did till SHM,
okay.
but now waves and sound is remaining.
So I'm going to start wave optics next lecture. Yeah.
But that are different chapters, right? Wave and sound and wave
So
optics.
see if you have finished the wave and sound, you will find wave optics very easy.
But that I haven't completed. I did till SHM.
SHM, okay.
Uh,
So continue. SHM is also SHM is also good enough for me to start the wave and sound. Sorry, wave optics.
okay. Okay.
If you know the idea of sinusoidal wave, that is good enough.
Yes. Okay. Okay.
So those who have not gone through it, I'll suggest that by next lecture try to finish the first 2-3 lecture of SHM. That is sufficient, I think. In SHM, how many lectures do we have?
We have 6 lectures.
Okay, that's too much. Okay, fine. So try to finish as much as possible. SHM is not difficult because we have been solving in chapters, right?
Yes.
So if you watch it, you won't find it difficult at all. Okay. Bye guys, take care.
Thank you,
So
sir.
I'll announce on the group, don't worry. I'll announce about the lecture. And if you take more time, then we may start on next week. We can cancel this week and we can start next week.